Good afternoon, YouTubers. Today is Sunday, and it's a great day to review our knowledge on moments. And how about a crane like the one shown on this picture, which is asking for a free body diagram and so forth. So we have a crane here that is supported by some outriggers A and B, meaning that this is sort of like we draw this in a 3D sign, so that's A is gonna have another one here, another these jacks, um, taking care of the whole weight. So we got two on the A side and also two on the B side for stabilization of the crane. And so what else we have? If the crane and truck have a mass of 18 18 megagrams, so that means a force here like that, and at G1, and the boom has a mass of 1.8, and that's center of mass is G2 right here, and we have another force. It says here, determine the vertical reaction at each four outriggers as a function of the boom angle theta. So we have an angle here, theta, and the mass and the load. This is the load here. Is about 1.2 megagrams. Plot the results measured from theta to the critical angle where tipping start to occur. In other words, if you drop this too much, like this theta increase more than what is required to keep a force still active here, it will tip over. So that's not good. So you keep lowering this to that theta, let's call that theta critical, then the whole thing will tip. And there's a lot of videos of cranes doing that kind of weird things in where they tip over because of many reasons, that they don't estimate properly what is the weight here of this, and that create problem. So the idea is, when the force at point A is 0, then this thing is over, it will tip. So what's the free force diagram here? If I draw, let's see, actually let's do this better. Let's do sort of like a box here. That's the box, and that box has for example a force here, and it also has a force here. Let's call this force FA, and let's call this force here FB, and the force coming down is called a G1. No problem there. And what else is also happening? There's a boom, the boom sort of connected here, that is doing like this, and that boom has another force here coming down, and a force here at the tip also coming down. And we got this distance here, 6 meters and 6.25 meters here. These are meters. And here's the story. Let's see. And the distance, the important distance here, it says 2 meters from here. So that distance there is about 2 meters. 1 meter here, and about, let's see, another meter here. So the total distance from here to here, that would be 4, because this distance here is 1 meter as well. So that's 4. Now that kind of give a kind of a perspective of the forces involved. Let's call this G2, and for the sake of the argument, I'm gonna call this G3 as well. It doesn't matter. So this is the story. Let's see what else we got here. So let me redraw this. G1 doesn't look too good there. Actually, let's put here G1, and now let's draw back again the boom that is gonna disappear on me. So that's it. So we got G1 coming down, a G2 and a G3. And so let's start to work on this concept that when that theta degree will this tip over, at what theta thing critical this will tip over. That means that the force here at this point is 0. I can certainly do this two ways and or many more, but let's start with the sum of the forces on the y direction and y on the y. There's no x direction here, there's no force. If I draw my x, y and x coordinate, there's nothing, I don't see anything on the x direction. So in other words, if I have something like this, a force like this, then definitely it's going to be both in y and x, but not on this problem. So this problem is basically the forces on the y direction, and let's assume that positive up has to be 0. And for equilibrium, that means that FA plus FB, they are going up. Then what's coming down will be minus G1 is coming down, minus G2 and minus G3, and all those things have to be 0. Now careful here, we need to also, there's too many unknown. I mean G1, G2 and G3, they are defined within the problem, but FA and FB are not defined, so we need to look for those. Now I can take a moment right here, and that will eliminate FA. But I don't know, there's a little bit of a problem because I don't know theta. And why I need theta? Well, you need theta because as soon as you try to get the moment from point A, let's draw point A right here, that's point A. There is a distance from here to here that is known. That distance is 2 meters. Now here, then there's a force somewhere here acting. You don't have problem with G1. G1 is well defined. The distance will be 2 plus 1, that's 3. It is this force that's gonna cause trouble, because then you need to find out from point A what is the actual distance of this coming down of G2. So that distance have to do with, let's get here, let's form a triangle here. Then you need that distance, or you can get the triangle here as well. So based on this theta, because you don't have to deal with this, otherwise you will do something else, like this is 90 degrees and you get another here. But this let's work with the data the way it is. That's theta there. So what is this distance? Let's call that distance x1. So that distance x1 then have to be added to this whatever distance is here, which is about 2. So let's get that straight. So that distance I'm gonna call it x1 for that force coming down, which is in this case G2. Now what happened with G3? Well, it's the same. Then that's more of a distance. That distance would then have to be calculated from here to up here. And the nice thing is that you can get that back again from here as well. That's another triangle right there, which has to do with the theta. So let's work on x1. That distance x1 is simple. 6, which is the hypotenuse, time in this case will be the sine. So that would be 6 times the sine of theta. That would be x1. And x2 then will be the sum of these two guys, because this is the longest distance, so that will be 12.25 times the sine of theta. So that x1, and now let's call this x2. So actually x2, let me redraw here. x1 is from here to here, and this is x2, just to be careful here, right? Because I add the total length of the boom was added. And up to here, from here to here, according to the information, is 6, and I have another 6.25. So the total here then will be 12.25 times sine of theta, which I don't know what it is. Now, why these two things are important? Because then when we take the moment, let's say that we're going to take the moment around A, positive direction, and we are right here. So we're going to take the moment there, meaning that moment equals 0 equal Fa. I don't care because there's no arm there, so that's 0. That Fa is not important. But how about G1? Oh, G1 is important, and G1 is coming on the positive direction. So let's see what we have here. G1, that would be G1 time the important distance, that would be 2 plus 1, that would be 3 meters, and it's going on the positive direction. How about FB? FB is going the opposite direction, counterclockwise, so that would be FB times 4. I don't know what is FB. And now we have to deal with G2 now, but G2 is going on the positive direction, so that's G2. Now here is going to be the problem. The problem is, what is the arm of G2? Well, the arm will be this distance, which we know is x1, plus whatever distance from here to here, and that's 2. So I have 2 plus 6 sine of theta. That will do. How about G3? Well, G3 plus G3 parentheses, that would be again 2 plus whatever this distance, which is x2, and I define that, so it's 12.25 times sine of theta. Alright, so let's kind of wrap up this. G1 times 3, G1 is a force and it has an arm of 3. FB has an arm of 4 and it's going in the opposite direction. And so basically what is left is G2 times the length of the arm here, as shown here, perpendicular to A, and so this one here as well, which is G3, and we got everything there, except that we need to know what is, in this case, what is G1, what is G2, and what is G3. But they are well defined within the text of the problem, and the text said for the total mass of the truck is 18 megagrams, so that would be 18 times 10 to the 6 grams divided by 1000. Let's do this not that quick, not that fast. So let's say 1000 grams is 1 kilogram, so we understand what we're doing. 9.81, because that's mass, we need Newton, and this is meter second square, so that will do. Gram will cancel with grams, kilogram, meter second square, that's Newton. So we got a number here. Let's pop a calculator here. So that's about 176,580 Newton. That will do. How about G2 and G3? Let's see. G2 equal 1.8. Let's see if I remember that right. G2, G1, the boom has a mass, and the boom has a mass of 1.8 megagrams. So 1.8 times 10 to the 6 gram. We do the same. 9.81 divided by 1000, and that will be 1.8 times 6 times 9.81 divided by 1000. That's roughly 17,658 Newton. How about G3? G3 is the weight of the load here, 1.2 megagrams. So that's 1.2 times 10 to the 6 grams times 9.81 divided by 1000. That's roughly is 11,772 Newton. All right, so we define all the forces involved here. Let's drop this a little bit smaller so I can see everything and where we are. And so we have two equations here. one equation, it says that the moment around A, this has to be equal 0 eventually, and all the sum of the forces on the y direction needs to be equal 0. But there's a problem here. We have how many unknowns between those two equations? Actually, let's wrap this so you understand what I'm saying. Let's copy this equation. Oops. Let's copy that equation right here. And let's copy the moment equation, which is this one here. Let's put them. And we're gonna paste this here. And let's see. All right, there we go. So let's see how this looks like now. This is what I'm saying. We have as unknown FA, we don't know what it is. How about FB? We don't know what it is. But how about theta? We don't know theta either. So 3 unknown, 2 equations, that's not good. But then there's this issue about trying to get that theta that caused the tipping to start, and that would be sort of the maximum angle, because then they ask later on to plot the result as measured from theta equals 0. That means that the boom will be like this, and obviously the loads will be coming down like this, right? The load G2 and this load as well. But that would be 0, but then this will increase until you get the critical theta, which force in A will disappear. There's not going to be force in A. So that there is the hint to say that when we are looking for that theta critical, then the really unknown are FB and theta critical. So we have 2 equations to deal with that, and that can be solved. Like for example, if FA is 0, then we know that we're gonna have is FB equal G1 plus G2 plus G3. That's it. Now when we know FB, then we can use the moment equation here and solve for theta, and that will do. So let's calculate FB one moment here. FB will be then, let's see how what that be. That would be 176,580 plus 17,000. Got that number somewhere here. 658 plus 11,772. So that FB, I'm doing that in my calculator, that will be about 206,010 Newton. And remember that under this condition, FA equals 0. That's because of the tipping, calculation. Now, so we know that FB now, and we know everything here. Let's work on the moment equation so we can work the whole details here. Let's see how this will looks like now. So let's work on this one. So minus FB times 4, that's the arm. Now let's get all this back there on the positive side. That would be plus G1, and G1 is 176,580 times the arm, which is 3, plus G2. And what is G2? G2 is about 17,658, and that has to be multiplied by 2 plus 6 sine of theta, close the parentheses, and finally G3 plus G3, and that would be 11,772 times the arm, which is 2 plus 12.25 times sine of theta, close the arm, and all that has to be equal 0. So that's the idea. So now let's do a little bit of math and let's see how this end up being. Hold your horses here until I get this straight. So okay, so that will be minus fb times 4 the arm. Now everything that is number, you can have it like plus parentheses 176 times 580 times 3 plus this times this plus this times this, close parentheses, and then you have, then the anything left is the part that is with the sign. So that open a parenthesis, that would be 17,658 times 6 plus 11,772 times 12.25, close parenthesis, and that has to be multiplied by sine of theta equal 0. Now that's easier now to work on. So the numbers more or less will end up something like this. I'm gonna take this to the other side, so that means it's gonna be positive fb times 4 equal, now if we add all these, hold for 1 second here, I'm gonna do the math. I'm gonna pause the video and jump to the number. Let's see where we are. It's about 588,600 and plus 251.56, and that's going to be by the sine of theta. If we divide by 4 everybody, so we end up that FB is equal 147 150 plus 62 539 sine of theta. All right, wow, that took a while punching all those numbers. So now here's a story. We are trying to solve for theta, and that's what happened when all the force is held together by the FB, and that's going to be this force shown here, 206 at that critical angle. So we know FB, so FB is 206 010 equal 147 150. Well, let's draw this number better, that's ugly. 147 150 plus 62 539 sine of theta. So sine of theta equal, this will go here, so 206 010 206 010 minus 147 150, all that divided by this guy, 62 539 sine of theta equal, calculator here, let's see what that looks like. About 0.94 1 at the most, maybe another 1 and 2 here. So theta is the inverse of the sine. About 70.3 degrees. So that's basically it, and this we call it theta critical. So when this boom, if this boom here, if you drop it to about 70.3, the force here is zero, no force. You can stick your foot right there. There's not going to be any problem. In fact, you stick your foot there and lift it, the whole thing will crash. No good, right? But any angle below that, then you stick your foot there, it's going to be a problem for your foot, definitely. So at 70.3, that's where the whole thing will tip over. And the question that the problem is asking, can you plot the result from theta equals 0 to the critical angle? And you can calculate both FA and FB using the sum of the forces in the y direction. So just for the sake of the argument and time, I'm gonna work only perhaps on FB. FB is equal, as shown here, 147, 150 plus 62, 539 sine of theta. So let's see. When theta is 70.3, then FB will be at the maximum allowed for tipping. So when theta start to drop, let's say theta is 0, then the minimum force is 147, 150. So this looks more like this. If we do a draw, and theta is on the x-axis and FB on the y-axis, when theta is 0, sine of 0 is 0, so this is 147 here, 147, 150. Now when theta get to 70.3, then that's when you're gonna get the maximum force in FB, which is basically, we calculate here already, 206. Let's put it here somewhere, so this will look more like this. So here you are, and as any value within these two values will look more like a curve like this. There we go. So that's basically how that plot will looks like for FB. You substitute FB here, this FB now on the equation for FA, like for example back here on this one, or what else, where should I do that as well? I'm looking for where I have FA. Only there. So you have to rework this equation and substitute FB for what I already have in terms of sine, and then you will have your FA equation as well, and you can plot that equation as well. The important thing, what's the moral of the story here? The moral of the story is be careful with the moments. Like for example, in this particular case, this looks more like this, and actually like this. So there's a moment happening here with respect to the boom. Let's exaggerate. Let's say that I have three vertical forces like that for some reason, and but I'm taking the moment. Let's delete this equation. I'm taking the moment somewhere here. So the important thing is that distance, like for example this distance, call it x1, this distance, call it x2, and this distance, call that x3. See, that's the important thing, because then you are taking a moment here, and the only thing that you care is like these forces are going straight down for this distance, creating the torque or the moment here, in this case clockwise on this and this and this one. So, and like for example, you can make your own problem. Let's put a force here somewhere, and that force actually Uh, let's see. Let's delete that one. Well, you can put it anywhere. Well, yeah, let's put the force here, and then you remember that you have some other forces here acting as well. On that, if you have the distance, then you can take the moment around A, and basically it was the story of our problem, just to trying to get those distances, you know, because based on the fact that there was a theta here, and you were able, based on the the distance as shown here, for where the forces within the boom are happening on the bar or the boom. Well, folks, that's basically it. I have nothing more to say except that you keep practicing this type of problem, because they're kind of interesting, and it's kind of interesting also to see some videos of the crane tipping over, because this is no joke. Um, um, for example, you and this happened. I mean, I have seen this many times. A car fall into a lake, and there's a crane is gonna try to get the car out. They kind of estimate the car weight, but they forgot that it's full of water. And when they try to lift it, on the calculation, you can see that the crane kind of tip over and it's gone. It's gone right, drop right into the lake as well. Sort of like this kind of a scenario where you have the crane. The crane is right here. Let's put a crane here, and it's trying to lift a car that is on a lake here. On the car, some is here, right? And so you are trying to lift the car from here, but that car is also full of water, and the load here is is definitely greater than what you estimate with the car alone. And so you got to be careful with this kind of a situation, because definitely it will create a problem. And so, you know, this is where the crane is located, but it will easily tip over because the load here is beyond what the pilot and the crane estimate. So be careful with that. It's a very interesting problem, and I have seen it failing many times, about when they overload and put a, a higher load here, that at the angle that than this can go. But remember, that's what we're talking about, this angle here. When this go beyond that angle, the force here, this will tip over very easy. As I always said, have fun whatever be your final destination. Have a great day. Bye.